Hi there. In this video, we're going to be looking at examining chemical equations. There's a couple of different terms we need before we can start examining these equations. The first is coefficients. Coefficients are the numbers that go in front of elements or compounds. These change the number of that thing taking place in the reaction, or taking part in the reaction. But they don't change the formula. Think about coefficients in math, like 3x or 2x. That 3 or 2 is what we're talking about here. Subscripts refer to the number of each element in a compound. So these do change the formula of that compound. These are set. These cannot change from reaction to reaction. And finally, we have some states of matter. We can denote the state of matter or the phase of matter in a reaction by using some symbols. Solid is shown with a little s, liquid shown with an L, gases shown with a G, and finally aqueous, meaning dissolved in water, shown with an AQ. Aqueous should be spelled like that. So we want to denote the state of matter. We want to denote the number of atoms in a compound with the subscripts. We want to denote the number of things taking place in a reaction with coefficients. So let's look at a reaction. Here's our first reaction. We have a liquid that starts off yellow and ends up brown. This reaction is actually this right here. Chlorine reacting with sodium bromide to make bromine and sodium chloride. I want to point out a couple of different things. We've got a subscript 2 telling you that there's 2 chlorine atoms stuck together. We have a coefficient 2 telling you that you have 2 separate sodium bromides. And same thing on the other side. A subscript 2 telling you you have 2 bromines, and a coefficient 2 telling you you have 2 separate sodium chlorides. We don't yet know the states of matter, but we can take a guess that some of these things are probably liquids based on what we saw in that reaction. Let's look at another reaction where we do know the phases of matter a little bit better. You may have seen this in class before. We have a piece of copper wire that we're putting into a solution of silver nitrate. Over time, that copper and silver will switch places and will form some copper nitrate and solid silver. This is all solid silver you see forming on the wire there. If we look at the reaction, it looks something like this, where you have copper metal that we know is a solid reacting with silver nitrate. We know it's a solid dissolved in water, or is aqueous, to form solid silver and aqueous copper nitrate. Notice there's some subscripts telling you the number of oxygens in these nitrates, but there's no coefficients, so we have nothing to modify the number of things taking place in this reaction. The final example we have is a magnesium ribbon put inside a solution of hydrochloric acid. And notice these bubbles coming out of it. That's hydrogen gas. So again, we can assign some states of matter. We know the magnesium is solid. We know the hydrochloric acid is aqueous. The magnesium chloride that forms is also aqueous. And that hydrogen is a gas. Notice here we have some subscripts telling us that there's 1 magnesium to 2 chlorine atoms, that's that compound, or H2 telling us it's 2 hydrogens stuck together, and we have a coefficient, HCl, telling us that there's got to be a hydrogen and a chlorine, but 2 of those. So the next question is why? The law of conservation of matter tells us that matter can neither be created nor destroyed in a chemical reaction. That is to say, all the atoms you start with need to end up as products. How does that happen? We use coefficients to change the number of particles taking place in a reaction to make that reaction balance. That is to say, we can't change the subscripts. We can't change what the compounds are, but we can change the coefficients to make these things balanced. A couple of quick terms. Atoms, these are the basic building blocks of matter. This is what we're rearranging in these chemical equations. Molecules, two or more atoms of different elements combined together. Oftentimes the compounds we see will be molecules. Sometimes they're ionic compounds. And this is going to be the same definition as a molecule, but in this case, it's going to be two or more ions of different elements combined together. For right now, we're not super concerned about the difference between molecules or ionic compounds, but recognize there definitely are differences there. Finally, we want to look at what are called the diatomic molecules. As the name suggests, di meaning two, these are elements that exist as two atoms chemically bonded together. We see some examples over here. We see hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Whenever those elements are by themselves, they must exist as that element with two bonded together. A good way to remember this is you can rearrange the order of those elements to get an acronym that we pronounce Hofbrinkel. So sometimes we hear these referred to as the Hofbrinkel elements. For the second part of the lecture, we want to look at representing reactions. And there's three different ways that we can represent reactions. We can represent them symbolically with equations. We can represent them on a macroscopic level, that is what we see or can look at in lab, or we can represent them on a particulate level with some drawings. So let's get some practice with that right here. I want to draw particulate level models for the following. Br2, this is bromine. Bromine is one of our diatomic elements, so we see it existing as two atoms stuck together, which we can represent as two bromine atoms stuck together. Sodium iodide is a sodium atom and an iodine atom. Again, not something we're going to touch on, but these are actually ions. Calcium carbonate, primary component of limestone. Draw calcium, one calcium. And then CO3, we're going to draw one carbon and three oxygens coming off it. And again, these are ions, but for right now, we're not concerned about that. We're just concerned about representing it. For these last two examples, I want to combine our particulate models with balancing equations. Here we have Br2 that you drew earlier, reacting with sodium iodide. And notice there's two of them. We'll draw two to form iodine and sodium bromide. So I want to count up our atoms. And if we look, I see two bromine on the right, but only one bromine on the left. I see two sodium and just one sodium, but I do see two iodine and two iodine. So I know, based on my particulate model, that I've lost some sodium and lost some bromine. The way I could fix this is by putting a 2 in front of the sodium bromide. Then I could draw in another sodium bromide. And now if I count up the atoms on both sides, I see that there's 2 sodium and 2 sodium and 2 bromine and 2 bromine. Notice I didn't change the identity of the compounds, just the number of them taking part in the reaction. The final example reads nitrogen and hydrogen combine to form ammonia. Nitrogen is one of the Hofbrinkels, hydrogen is another Hofbrinkel, and they're combining to form ammonia. Now the problem doesn't state it, but these things are likely all in the gas phase, so we'll put small g's next to them. If I draw a particulate level model, I see nitrogen reacting with hydrogen to make ammonia. What do you notice about the atoms? Do you notice that there's 2 hydrogens and 3 hydrogens, and 1 nitrogen and 1 nitrogen? That is to say, our atoms don't balance. So what we need to do here is change the number of things in our drawings to make these atoms balance. What I'd suggest doing is looking at the equation and seeing that hydrogens come in multiples of 3 here and multiples of 2 here. So let's try 3 H2s and 2 NH3s, because that would give us 6 hydrogens on both sides. Let's draw that and see what happens. There's my 3 hydrogens, and there's my 2 ammonias. Now let's count up the elements again. 2 nitrogen, 2 nitrogen, 6 hydrogen, 6 hydrogen. Balanced. In review, we talked about subscripts. Those modify the number of atoms in an element in a compound. We talked about coefficients. Those modify the number of elements or compounds in a reaction. We talked about the conservation of mass and the need to balance equations. And finally, we talked about adding states of matter, solid, liquid, gas, or aqueous, to tell your reader a little bit more about the equation. Thanks for watching.